Good morning, good afternoon, good evening. It's Juancho here. Computer graphics. That's the topic today. We are going to go on an adventure. We're going to learn how computer graphics are made. By the end of this course, you should be able to pick up any graphics API and understand how it works and make computer graphics. These slides are available on Google Drive. Please don't distribute these without prior written permission and an acknowledgement that this material has been copied from the excellent lectures that Dr. Shaw has prepared, and I will be following in the course that he does in Boston. In 1986, I had just finished my first computer science graphics course, and this movie came out. And the two of those things together kind of got me excited about computer graphics. This animation got an award, actually. Let's have a look at this. Why I got into computer graphics. And here's the Pixar Studios, and they have an homage to this. Ed Catmull was one of the original computer graphics people, and he wrote what is considered to be the computer graphics pipeline that we have been implementing ever since back then. My thesis referred to him, and a lot of people have worked with him. He's just an all-around good guy. You can watch more on Pixar, on their history, and all of the aspects that go into making the movie, which are math, science, art, and all of the code that goes there together. Every movie that they release pushes the boundaries of computer graphics. It's actually a really fun video to watch. Okay, who am I? How are we going to do this course? What are the rules of engagement here? Who am I? Well, 1976, John Loader, my math teacher, got an account at the University of Sussex, and he was all excited about programming. And we wrote these programs on these MarkSense cards, which look like this card here. We would fill them out with a piece of paper, and then we mailed them in, actually put them in an envelope and sent them to the University of Sussex. And I got mine back 2 weeks later, and mine said syntax error. Everyone else actually paid attention, and they got their program to run. I thought programming sucks. I didn't even know what programming was then, but there we go. That's what it was. Where have I been? I finished went through a whole bunch of school, finished my PhD in computer science, and then I taught at the University of Alberta for 5 years. Then I worked at Electronic Arts for 8 years. Then I went to Carnegie Mellon, where I did some game sketching, researching on how to prototype interactive environments without actually writing big game engines. I then went to Amazon because I was interested in how big data is handled and how these large systems work. I work for Amazon Retail, AWS, and Alexa. Those are actually the three Amazons. I also work for two relatively smaller companies here in Vancouver, Hothead Games, that does casual games, and Staffbase, which is a kind of corporate communication company. I will be making all of the materials available on campus. The office hours and all of that will be updated. At this point, I don't have any TAs, but my course is available. We will do this in class, so you can prepare for this. The syllabus is on campus, and it will be updated as we go, but we're mostly following Mike Shaw's work. We're basically showing you how the basic graphics pipeline works. And by the end of this course, you will be able to talk about the basics graphics pipeline and understand how it applies to other APIs such as OpenGL, Vulkan, and Metal. And you will have built a scene renderer that can render an animated interactive scene of some sort, and that you'll also have built a project that is no bounds on what you can do with that. This is an interactive learning session. I'm your guide. I expect you to read the materials and to watch the videos. We will be trying to do as much coding as we can in the class. We have a very small class, about 10 people this year, so I'll be able to spend time with you and go and sit with you and look at your screen. Kittens, that's what it's all about. Oh, there's big kittens there, little people, I don't know. Teamwork. The way that it works in the real world is you write your own code, you solve your problem. People around you are not writing the same code, they're doing something else, but they will help you. So I expect you to work in kind of the same way, talk to other people, talk to them about your code. If there's anything that you discover that you feel can share all of the students, that's good. This is a grad level course, and I expect all of you to do very well. And the more that you help each other in terms of sharing solutions, or if there's particularly, if me, the professor, if I hand out some bad code and you find a bug, I'd love it if you just tell me what it is and you share it with the team. We're going to be using laptops, Mac, Linux, Ubuntu, Windows. I personally have Visual Studio on a Mac. I will be doing the programming in WebGL. You can also do them in C++ and OpenGL, but I will not be supporting this. And one note here, please, please, please bring your power supply. Working on this code in the classroom is extremely important, and I want you to participate. And I do not want to see people drop out of class because they have not brought their power supply. Basically, if you lose your power supply, I will consider it as if you're not in the classroom. There's no required text room, but the internet is full of very, very good and comprehensive overviews about how OpenGL works and graphics. There's also guides from Metal and Vulkan. We are going to be using WebGL, so the WebGL programming guide that is there it will be a useful course. There's also the WebGL 2 Fundamentals course. And OpenGL, you'll see, is very similar to WebGL. The more modern versions of OpenGL have added features to it, but learning WebGL prepares you for all of this stuff. And then the features that are available in 3 and 4 will actually make sense to you. There is a very extensive set of resources from Mike Shaw, who has an OpenGL playlist and an STL2 playlist. And once you start looking at those videos, you'll see that there's an extensive amount of setup that needs to be done to do the graphics in those, and WebGL has actually made those simpler. There will be lectures. I will cover a shorter version of these videos, mini visuals on the slides, and then we'll do in class labs. It's a very hands-on class. We're going to build things. I'm going to make mistakes. You're going to make mistakes. We stop. We ask questions. I want to help you. I want to celebrate you getting the best possible grade you can in this course. And the only way we can do that is if we have a shared experience. These PowerPoints are really dense. That's intentional. I love the way that Mike Shaw put them together, and I've made some additions myself. But the slides should be available as a resource to you later. You can follow along with the slides, the video, but they are a resource for you. How do you contact me? Piazza. If you're asking a question that you think other people may share, ask it generally in the whole group. If you have a personal question, you can email me, or you can post a personal IM on Piazza. Teams IM only for emergencies. An email, I really don't spend a lot. I don't want to be dealing with emails. I have a lot of emails coming in, and I'd like to segregate and have a place where I go to help you, which is Piazza, and that's where my day. I start with Piazza. I look to see if there's any issues. IMs only for emergencies. If I get an IM that doesn't look like it's an emergency, I will ignore it, maybe respond the next day and treat it like an email. But emails, it's only good for like documenting or something like that. Yeah, Piazza, we should be registering it. I already talked about that. On the weekends, I will check in, but you'll notice that I've made all of the assignments due Friday. I don't want you to be working over the weekends. You probably have other courses, or you may actually have a life and do something. I encourage everybody to continue to start building a work-life balance, because that's going to be very important for you throughout your career. again, we talked about Piazza, public posts, share with people, ask questions, and again, reminding you about Microsoft Teams, that it's an emergency. When you are struggling with wellness issues, please reach out to me as soon as possible, and that would be appropriate for email or for office hours conversations. Yep, we get this a lot. I'm in trouble, help me. Yes, you have 3 tokens in this course that you can use for a 1-day delay on a assignment. More details on that will be documented. You are going to hopefully not use them. If you do use them, you can use just there's a way for doing it. Otherwise, be proactive. Ask for help early. I've had so many sad situations in the past where a student says, I wish I had reached out to you earlier. I'm like, why didn't you? Well, I just wanted to do it myself. I'm like, well, I'm here as a guide. I'm here as a resource. I'm here to make sure that you have the best learning opportunity that you have. So I'm your resource. You pay for me to be here. So you should definitely use me as a resource. This is going to be a heavy duty course because I want you to do a lot in this course. Linear algebra, you should have taken that course. If you are rusty on that, I will do a review on it. Data structures, when I say something like insert something in a linked list, I should expect it. And I would expect that the code you write is object-oriented. TypeScript supports objects and classes. And I really hope that you use the same IDE as I am. But if you don't, that's fine. My ability to support you will be increased if you go and use Visual Studio, etc. We are going to be doing it in TypeScript. You may or may not have seen TypeScript. TypeScript is a modernization of JavaScript. The elements of the language that you're going to need are very straightforward. And I will be giving you a working framework in the Agile methodology, and then you will be editing that, so you won't have to be doing things from scratch. But you don't have to use my code. You might want to. And every assignment will probably be building on the previous one, so we'll have the solution to the previous assignment, so you will have working base. You can continue to work with your solution or my solution, or you can merge the two together. It's entirely up to you how you do that. Here's some resources. I expect that you will be curious about OpenGL. There is an excellent set of alternate videos from Yem Yuxel at the University of Utah. He also uses TypeScript or WebGL. He does the course in a slightly different order. Where appropriate, I will link in the Canvas to the videos that are important from his particular set of videos. This is a course for people who don't know about computer graphics. And computer graphics is used a lot in games entertainment, but it's also for people in visualization, computer graphics, virtual reality. The recently failed metaverse was all about computer graphics. If you're interested in computer graphics and you want to know how it works, then this is what you are going to be studying and learning and mastering in this course. I want you to be able to get a job in computer graphics if that's what you want. And I want you to understand what a vertex buffer is and what a texture unit is. And I want you to be able to understand how those things come together to make a video game, a visualization alternative, something like Thingiverse where you can visualize the objects that are there. Just let me know what you want to do and how I can reach your goals. Here are some examples of graphics engineer positions. You'll notice that a lot of them don't specify what language. Some of them do. In this particular posting from Unity, you see one is a graphics engineer, and the other one's a graphics engineer with C++. As you can see, you don't necessarily have to have C++ to become a graphics engineer, and C++ is something that you'll be able to pick up later, and when you mesh the two of them together, it will make a lot of sense. Now, we're going to be doing a lot of code, and it's new to you. Don't spend 2 days coding and then try to compile. The basic way to develop is to write small pieces of code, run it, and test it. Some of the assignments that I will be giving you tests, and you'll be writing code against those tests. Get into the habit of writing test-driven development. Write your tests first, and then you won't get into the trouble where you have hundreds of compiler errors and trying to debug it all. A little bit at a time, always working software will help you a lot. So what will we learn in this course? We're going to be real-time rendering with modern WebGL 2. Why WebGL 2? Because it's the same concepts as OpenGL. It's actually OpenGL 3, and it's easy. It basically uses the GLSL, the shading language 3, and OpenGL 3 and 4 has extended and added more features to it, but the basic concepts of how you set up an array of vertices to render, how you use textures, how you do lighting, it's all the same stuff. So we will do that. And if you go to this website here, you'll see that Google Max Terrain View, Architecture Visualization, Game Engines, Unity and Play Canvas, and Modeling in SketchUp, Google SketchUp, they're all using WebGL to build these interactive applications. So it's a very powerful API, and you're not going to be, it's not a second-class API. Here is a full downloadable version of a good reference book for this. And so let's do our first exercise. This is the course. We're going to, of course, we'll do this in the course. And I want to see that. We're going to go around the classroom and say, well, why do you want to do computer graphics? What is your story? Do you want to make a game? Do you want to do visualization? Or are you just curious for this process? We are in a world where there is full-blown graphics libraries that we could just use. But we're going to do things from scratch. We're going to start with a simple triangle, a very, very simple triangle, and we're going to make it up, and then we'll add more triangles, and we'll show you how to render several triangles, and we'll add some textures to those triangles, and we'll add lights to those triangles, and then all of a sudden, boom, things will get bigger and bigger, and you'll see that we can start to deal with that. But these baby steps will get us there, and the reason that we're doing that is so you can understand how the whole thing works, because modern computer graphics is all about data management and setting data up for this very specific high performance hardware that you have to set stuff up in a particular way to make it really, really scream. So I always say computer graphics is computer science, you can see. Computers allow us to perform an incredible amount of computations. And as you'll see, the computer graphics computations are actually really, really simple and really straightforward. You just have to do a lot of them. If you do a lot of them, you have thousands of polygons and lights and reflections. You can have some really, really complex worlds, and you can alter and create those complex worlds, and you can produce dynamic and interesting worlds. You can synthesize 2 or 3D images. You might actually do it completely from scratch, or you might manipulate some photos in terms of textures, or we were going to combine the two of them together. So what we're looking at is the very beginning part of the journey of computer graphics. We are going to focus on 3D rendering. There's a whole bunch of 2D stuff that has come to light in terms of manipulating images and merging them together and creating new images from that, and you can go play with that on Midjourney or DALL-E. We're not going to be focusing on that. We're going to be focusing on 3D computer graphics. The domains, these are the domains that computer graphics can be used in: 3D modeling, rendering, animation, user interaction, virtual reality, visualization, image processing, and 3D scanning, just to name a few. So 3D modeling, It's the process of building within a computer these 3D models. You can extrude things. We'll do a little exercise in OpenSCAD in this in this particular first lecture, where you'll see where you can actually experience kind of what it is like to model and think about things as models. And one of the assignments, you will actually contribute another object to the data that we have for this course. There's a whole variety of different tools that have been built for this. Over the years, the industry has been driven by these tools, and the power of these tools has grown as the computation grows. If you remember, we go back here where I said computers allow us to perform large numbers of computations. So as computers have been getting faster and faster, the complexity of the objects that we can render has gotten more and more complex. When I first started doing computer graphics in 1986, I was working on a PC-AT 286, which, I don't know, had like 64 kilobytes, maybe 128 kilobytes of memory. The laptop I have right now has 96 gigabytes of memory. So the complexity of the data that I can hold in core now is monumental compared to where it was. So these 3D modeling packages have been able to allow you to produce more and more complex geometries such that the worlds that we're building get more and more complex. Rendering. Rendering is the process of taking a bunch of 3D objects and creating images. What we are going to be doing in this course, we're going to be doing rendering that can be done in a very short amount of time. For really complex computer graphics scenes like you see in the movies, like the ones you see here, you see a whole bunch of soft shadows, and you see like lights bleeding, and there's places in the scene where you can see something but there's no direct light on it because the light is bounced around in it. And then we have these rendering engines that can kind of iterate and make more and more complex images over time. That is a separate course. Ray tracing is something that can be done, and there's a whole field study of where they study how to render these graphics images, and sometimes they'll take 10, 15, 20 hours to render on really, really powerful computers. So we're not done yet, and as a graphic, but like I said, for this course, we're going to be dealing with the stuff that our hardware on our laptops can deal with in real time. And don't worry about it, because your laptop is incredibly powerful compared to what some of the computer graphics systems were in the past. So this is the real-time rendering that we will explore. We'll do normal mapping with a shading language that you'll see how we can write programs that compute the lighting on each little fragment of the image in what we call fragment shaders. You'll see that come up later. And then you'll see how you can make images look way, way more sophisticated than the underlying polygonal representation of that image is. And if you're getting overwhelmed by all of this, don't worry about it, because we're going to go through all of these things a little bit at a time as the course progresses. This is just an overview of everything that we're going to be doing. Animation. Once you can render an image in one place, then you can change that particular position of it, and then you can make another animation. An animation is just a bunch of frames, one after the other. So, when you make a movie, you have a camera that takes a shot every 24th of a second or every 60th of a second. And what we're going to be doing in computer graphics is we're going to be developing a model for our computer graphics objects, and then we're going to be changing their position and re-rendering them, and therefore we will be doing an animation. Your final project will be an animated world. The sixth assignment is the solar system revolving around itself, and you can see that. But yeah, animation is just still images one at a time. And the reason that we're focusing on real-time rendering is because we want to be able to do something that looks like it's animated without having to wait 1 hour per frame and then put them together. The way that that these these scenes work here is that every single frame is computed offline and stored as a file, and then those individual frame files are filmed together as frames of a movie, and then they're made into a movie such that you have that. What we're going to be doing is we're going to be making those frames in real time on our computer such that we can portray the idea of things moving around when actually they're not. They're just a whole bunch of snapshots, one after the other. And we will also look at particle systems. Particle systems are kind of fun. They're just little particles that float around, and they're generated procedurally, and you can make them change colors. You can also add gravity to them, as you see at the top there, or you can have them have a color map such that they're burning, and then over time they rise up, and then they turn into gray clouds, and then you see some cinders and stuff like that. And we're going to get to a point where we can see and do this as well as part of this course. And then user interaction. We're not going to be spending a lot of time on user interaction. There is a whole field of study of UI research and user experience. We are going to restrict our input to probably some mouse movement or some buttons, but there is a whole bunch of different interaction techniques that have been given. The stylus, as you see at the upper right hand corner there, is something that artists use when they're doing their modeling, because they can pull on things and they can push things and they can cut things, and you'll see that in the Pixar. You'll see some of the kind of screenshots of the Pixar video, but that's that. Virtual reality. Virtual reality is where you basically close off the world. You've all seen it, Oculus and stuff like that. But basically, you put the image, the user inside a virtual world, and then you track their head movement and in some cases their eye movement, such that you can look around and get like a 360-degree view. It's one of those interesting applications that's still looking for a consumer application. I personally don't think it will ever exist, but there are definitely people that are betting big on that. The latest company to bet big on that and not succeed was Facebook with Metaverse, but we are going to continue to see that. But the technology is really interesting. This is an interesting example of, we've built a technology, but we don't know what to do with it. There's no real application for it where masses of people want to do it. And just think about it. I think it's kind of cool, and you probably think it's kind of cool because you're computer graphics people. But if your mother's not a technical person, think about whether your mother would want to use this, or your aunt, or your grandmother, or your grandfather. These are the consumers who will define whether these technologies are useful or not. And so far, they have voted no, and it hasn't occurred. Visualization. We have a lot of data. When I started my numerical analysis course back in 1984, my professor said, never before in the history of mankind have we been able to compute so many numbers and we don't know what they mean. With the advent of computer graphics, we've been able to take this data. We have lots and lots and lots of data. When you fly a plane from Vancouver to Tokyo, it generates something like 4 to 5 petabytes of data from all of the sensors on board that they need to study and analyze to see how efficient the plane is and stuff like that. Lots of data, lots of data. How do you understand it? Well, it turns out if you display it graphically, you can actually help people understand. On the left-hand side, you see kind of the involvement of the different Queen band members and how they contributed to different songs. And then there's some more visualizations on the New York Times data visualizations where they visualize a number of different things. And you see this all the time, trying to help. Sometimes the visualizations work, sometimes they don't. Image processing. My PhD thesis was on this, where I was looking at 3D scan data, and I was rendering it. So we were able to see inside people. This is a very, very useful piece of research because we can actually show you things that you can't see normally. You just can't slice someone's head open to see what's going in there, but you can actually use MRI data, magnetic resonance imaging, to capture the different densities inside someone's head or their bones or their hips, and then they will be able. Then you can actually go through and see if there's anything that is useful or not useful. Image processing, this voxel technique, which was used for rendering data that we had scanned from inside a person, it's used in Minecraft, where a person actually wrote a JavaScript image engine that rendered voxels. It just basically rendered cubes, and it went on to be a phenomenal success of a game which was had such a simple and beautiful gameplay, and it still has a great following, and Microsoft bought it, and everything is still there. You want to we can take image filters and we can change the color of the images. We can change bloom. We can add color effects. There's a whole bunch of things that we can do to real-time computer graphics that we get from imaging. So there's, but again, we're not going to be doing image processing in this particular class. On the upper right-hand side, you can see kind of the effect of changing the focus on a camera, of taking a picture. On the bottom, on that little light that's glowing there, you can see the effect of kind of surrounding the light bulb with some gas, so you get this kind of bloom to it. But yeah, again, we're not going to, it's fascinating, but we're not going to be touching that in this course. 3D scanning. How do you get data for your models? Well, you can grab an arbitrary object, take pictures from a whole variety of angles, and then put them all together and get a mesh for that. Most of your phones now have an app for scanning 3D objects and uploading it. So when you get to the assignment where you're trying to upload an image for this course, that may be one way that you want to do it. You might have a unique thing that you would like to share with the rest of the class. You could share that, and then we can have a look at it and see if it's of the right kind of size for people to do it, etc., etc. So some of the places you've seen computer graphics is video games, cartoons, like Luxo, visual effects. Most movies that you see nowadays have some sort of computer graphics, CGI. There's full animated films. There's computer-aided design, simulation, medical imaging, informational visualization. These are all fields where you've seen some computer graphics applications. So real-time computer graphics, okay? Well, let's talk about that. We're going to focus on this in this course. Interactive computer graphics is a video game with 3D modeling tools, and offland is pre-rendered. We render one frame at a time, and we don't care if it takes 1 hour or 10 hours. It would be really boring to watch a Pixar movie with one frame at a time, because they run these large render farms, and then they will put them all together. And ray tracer is also something where it could take hours or require huge amounts of compute to produce the images. So we're going to be dealing with the OpenGL hardware graphics on your chip, on your computer. That's what we're going to be focusing on. And that is will propel you into being a computer graphics engineer. You will have all of the necessary knowledge that you'll need to become a computer graphics person at the end of this course. Interactive computer graphics, they're kind of fun because you're doing the real time. Your models are sufficient that you can do things in real time. The interactivity of your projects will get more and more interesting as you go through this course. And you'll notice about halfway through the course, it gets really exciting because we're actually dealing with things that look real and we'll start animating them, and it'll be kind of a lot of fun. Offline computer graphics, we're not going to do as we talked about it, but you can see on the bottom right that it takes several seconds. There you go. You can see that that image being rendered. That's one image that's being rendered for that whole one. Well, there it is, and it goes, and there it is. It's generated. Okay, this is the break in class. Okay, so graphics APIs. What are we talking about? An application programming interface. Okay. APIs are a standardization of how an application interacts with something like a hardware or a server or something like that. It's no magic to it. It's just there's an interface. If I want you to do something, I ask you in English, that's our API, and then you go do it. So it's just something that we made up for convenience. We have computer graphics programs that have two APIs. One is to get input from the user. In this particular course, we're going to be using the React web app, and then one API for drawing pixels. So where did it all come from? How did we get here? There are many useful APIs. There's APIs for writing files, etc., etc. So we have APIs for every operating system is a bunch of APIs. AWS is a bunch of APIs. Unity provides APIs for you. You write a code, and there's cross-platform APIs, web interfaces. There's way too many frameworks. Every week there's a new framework for front-end web development, and now there's Electron web single host. We may do something with Electron in this course. I'm still playing with it to see if it's better than using just an app. But basically, Electron is web with a host that's running locally. So it was the history of the APIs. There was no APIs for a long time. Basically, you got set pixel. And one of the ways you teach this, that I've taught this course in the past, is you start off with set pixel, RGB, alpha for transparency, and then you start building a software renderer on top of that. It's an interesting exercise to go through that, because it teaches you everything that you need to do. In this course, we're going to skip that low level, and we're going to understand how it works, but we're going to not talk about it. So 1980, there was no APIs. Steve Jobs in 1986 funded Pixar. There was a lot of 3D experimentation going on. In 1992, Wolfenstein is released. I hacked that game, and every enemy was a professor at the UBC. For a long time, we didn't have any specialized hardware. So basically, you had to process everything on your CPU, and we'll talk about that later. But pretty much every computer now has a GPU, a graphics processing unit, that takes a representation of triangles and processes them and puts them on the screen. Some of them have two graphics cards, etc., etc. So it all depends on how powerful you are. But for example, with my computer, I have a very powerful chip that allows me to use hardware rendering. There's the GPUs. 1995, the Verge Graphics Series you can now buy for 45 cents. In 1990s, SGI started developing GL. They didn't call it OpenGL, and they had their own API, and then so in 1991 they started building it as an OpenGL. That meant that they took their internal API and they pushed it out, and then at version 2.1 they had a programmable pipeline with GLSL. That's what we're going to be talking about. vertex and fragment shader shortly. And version 3 and 4 remove the old fixed function pipeline. Don't worry about that. It's irrelevant. We'll talk about it a little bit. And then we will talk about WebGL 2, which implements version of GSL 3.0. So we will do that. For this class, we're going to focus on one API. We're going to use WebGL 2. It's what the pros use. It's a subset. If you're using OpenGL 4 or Metal or something like that, these are all kind of extensions of that. But with WebGL, you will get the fundamentals of computer graphics and how it all works out. You can build your own software rendering library, and you can also learn about ray tracing. You can do that by yourself. There's a whole bunch of self-teaching stuff, or you can take Mike Shaw's course in the future at some point, or I might decide to teach it here. Don't know. But the OpenGL organization is Open Graphics Library. It's specified there. It's got a whole governing body, and WebGL was an implementation of OpenGL such that you could embed it in browsers, and most browsers now actually implement it. So modern OpenGL, here we go. We have some textured, and you can see that the surfaces around here look like there's missing things here. That would be vertex shaders, and all of these textures here. They're probably these stones here were probably a texture, and you have particles here. You probably have some wind simulation on this flag, etc. That's all available in the Unreal Engine. Water is a good litmus test. Like, how good does the water look? Does this look like water? It's not moving, but as soon as you start moving it here, it's like, wow, that looks pretty good. One of the things that I find particularly interesting is that the weather app on my iPhone now has computer graphics that simulates the current weather, and when it's raining, I can see the drops of water bouncing off the top banner. So computer graphics is everywhere. So the other API is DirectX. Microsoft, of course, was competing with SGI, so they invented their own, which was DirectX 3D. And so they kind of grew up with OpenGL in a similar manner. And you can see DirectX 7 versus DirectX 9 here, Mountain Blade, Fire and Sword, and you can see how the details get more interesting. The clouds get more shouting up here. It's kind of flat. This is all very flat world. The shades and the shadows here are more interesting. Again, DirectX 9, you see some fairly fantastic details here in terms of the shading of the clouds and the texturing down here. DirectX 11 added more features. You got this motion blur, this kind of out of focus rendering out here. Then you can see how much. So there's two things that have gone wrong. One is improvement in features, and the other one is in performance. And so a draw call per frame, this is how many batches. A draw call is a batch of vertices that is sent to the GPU. We'll learn about that, don't worry about it. But you'll see here that we are getting 5,760 draw calls per frame, and we're doing 79.8 frames per second. So multiply those two together, and you kind of get an idea of the performance of DirectX 11. Now look at this one here. We're running at 123 frames per second, and we're rendering more draw calls per frame. So we've increased the complexity of the scene, and we're rendering more frames per second. So you see how we probably added the ability to deal with more features here, more draw calls. The objects are more complicated, and we're doing it at 123 frames per second, which is just insane. Ray tracing. Ray tracing is where, and we'll cover it towards the end of the course, but we're not going to go into details. Basically, what you do is you shoot a ray through a pixel, it hits the mirror here, and then that bounces off there, and you keep doing that until you hit a light or something that's not emitting, and then you can say, okay, well, the color of this pixel right here is actually this pixel right here. Yeah, I think so. So this goes to there, and you see the color, stuff like that. But they're also changing the shape of the mirror, so you're getting different colors. So this is looking through the glass. I think it's that's looking through the glass, and that's not looking. So why are we learning WebGL versus DirectX or OpenGL versus DirectX? We got to learn something, right? OpenGL or WebGL runs everywhere. Both are equally. The goal of this course is to help you know how computer graphics works. And if you know WebGL, you can understand Metal, because the computer graphics hardware is all very similar. It's optimized for speed, not convenience. And so it is our job as computer graphics programmers to manipulate the data such that we can get the most speed from those things. And yeah, go ahead, learn OpenGL, Metal, DirectX, any one of these things. There's all sorts of tutorials online for those things. There's all sorts of things that are going to help you get this thing done and learn and understand how to do that. So programming graphics. Okay, so what we're going to do, we're going to use two programming tools to start with. We're going to use TypeScript, which is just JavaScript on steroids, and then we'll use the React Web Development Framework to deal with the input. There should be input there. Okay, let's just fix that right now. Okay, that's fixed. And now we go back to slideshow, presenter view, like that. Okay, now see that I told you I was going to make mistakes live in the class, and I can also do them on the video. Okay, so for the summary, today what we've done is we've covered the course administrivia. Work on your own. Ask me for help early. I'm here to help you learn. We talked a little bit about some of the domains of computer graphics. We talked about graphics APIs. We talked about why we're going to use WebGL and TypeScript. And what we're going to do in class following this video is we're going to get your React up and running, and we'll do the first assignment. We'll start working on the first assignment, and we'll do that over the course of the two lectures that are part of this assignment. And then you'll do, there'll be a quiz that you can do after this course. There you go. So the in-class activity is going to be a Canvas link that I will make that will be available at the end of the lecture. It will ask you some questions about this video that we've the preparatory stuff, and then it will also have some questions about the in-class lab work. Okay. If you did not watch this video, there'll be I would expect you to watch it after the class, because I'll just be doing a very, very kind of condensed version of this in class. If you do, I'll email, you'll get an email about this anyways. So there we go. And so what we're going to do is we're going to do Hello World WebGL. And so we're going to go through and see how that works. Ignore this. This gets deleted. And then we say slideshow, presenter view, like that. Things about Git. My code was not working, but I can't remember what I changed. You should never sit there and work for 4 hours at a time and then try to figure out what you broke. So the idea of using Git is that you try to have working code as frequently as possible. So change a line of code, get it working. If it's working, pass the test, etc. Check it in. And then do another one, then check it in. And then if you have something that's working and you do some work on it and then it's broken and you can't understand what it was, what you can do is you can just undo all of the changes back to when you know it was working and then get it back. You really shouldn't have one git commit in the repository before the assignment deadline. So you really should be doing frequent check-ins. My colleague Mike Shaw has got some videos on Git and GitHub. Really worth learning. You will definitely need to use Git and GitHub. They've become the de facto standard in industry. Some companies use slightly different versions, but the whole idea of having a history of changes that you can look at and understand how the code evolved, and also for yourself to protect yourself, absolutely golden. You should definitely work on that. There's a handout here that you can look, which will help you. I've seen this posted up on a number of engineers' cubes at work. And so let's go and have fun. That's the end of this video, I believe. And that's it. The rest of this is C++, which we're not covering in this course. And this will be the final, there we go. This is the final part of this recording. We're going to be using computer graphics to generate 2 or 3D images, and we are going to be doing all of the 3D. Okay, bye.